In this video, we're going to be looking at pressure and some general information about gases. So to start off, in order to understand all these ideas about gases, we need to think about kinetic molecular theory. The word kinetic means movement. So we're talking about the movement of molecules with this. Specifically with gases, gases are made of moving particles. And with that, so the molecules of gases, the particles of gases are constantly moving. And because they're so tiny, even if they get close to each other, they're still going to be considered really far apart. And so they're always going to be kind of distant from each other. They're also always going to move in a straight line and bounce off of each other or off the walls of their container. So they have what we call perfectly elastic collision. So if they were to collide with this wall with a certain force, they're going to bounce back with equal force and just continue their momentum. Or if they hit something else. And because as they move more, that's actually going to increase their temperature. So the higher the temperature, the faster they're moving. Now for what pressure is. So pressure is the force per unit area on a surface. So if you compare standing flat-footed compared to how she's on point, has less area that her whole body weight is on versus if you were to stand on your feet nice and flat, you're going to have a greater surface area for your foot to apply and for your body weight to be on. So you would feel more pressure on point versus if you're flat-footed. With a moving particle, so gases are moving constantly, and this particle, right, is going to be moving around, crashing into the wall, bouncing around as it hits. And each collision is going to exert a little bit of force. So as these collisions add up, as they keep going, they're going to add up to a fair amount of force. And that's what pressure is. So as they're colliding with the wall, as they're applying that force to the wall, they're exerting pressure. Now this is just showing one particle of gas, but remember there's going to be a bunch of them, trillions and billions of them. So we're going to be feeling that constantly. There's always going to be that pressure there. Now there's absolutely no particles at all. That's called a vacuum. And there's not going to be any pressure in that case. So actually in outer space, there's no particles, and that's considered a vacuum there, not just what you use to clean the floor. In order to measure pressure, we use a device called a barometer. And this is for measuring the air pressure around us. So how this works is we have a tub of mercury, and it has a tube. And the tube has little millimeter markings on it. So as the atmospheric pressure or the air pressure pushes down on the bowl of mercury, it's going to cause the mercury in this tube to go up or come down. So if it's applying force, we're going to see more mercury in the tube, causing it to rise up, showing us there's more pressure. So this is one of the reasons why the common unit for air pressure is millimeters of mercury. We also call this torr. Some interesting facts about this. We can actually use barometers to tell if a storm is approaching. So good weather, nice weather is going to have a high atmospheric pressure. And in a storm, the air pressure actually drops. If you ever watch the news, you will sometimes hear about low pressure systems coming in, and that means that there's a storm coming in. And And some people can really feel that, especially like as the weather shifts a lot this time of year. Like I'll get headaches as the storm's about to come. Like a lot of people just feel kind of off, and that's because of that low pressure coming in. Because it just changes our, like, what we're feeling in our atmosphere as well. And so they actually, you might have, or you might see around, old-timey barometers that actually will indicate, like, based off of the air pressure, what the weather is going to be looking like that day. So in chemistry, while we measure air pressure in millimeters of mercury, we actually talk about it in atmospheres. And ATM, oh my gosh, that was bad. ATM is the abbreviation for that. Now, if we are at sea level, that's actually going to be when we have our total atmosphere, and that's what we mean literally, like measuring the atmosphere above us. And so standard pressure is 1 atmosphere. So when you're in Santa Cruz, you're gonna have literally the entire atmosphere of the planet on you, and that's 1 atmosphere. There's other units, though, that we can use for pressure. In the United States, a really common unit that we use is pounds per square inch, or PSI. So if you ever like pump up a bike tire or a ball, you'll usually be reading that in PSI. So right, like a car tire is going to be around like 32 PSI. A scuba tank holds 3,000 PSI, so it's really pressurized. A dog bite has 400 PSI, and a great white shark has a 4,500 PSI. So that's a lot of pressure per square inch. So for us, PSI, because it's pounds is not an SI unit, inches are not a SI unit, we don't use them in science. So in chemistry, we're primarily going to use atmospheres, torr, and pascals, which we use PA for that. And typically we're going to deal with kilopascals because of how small pascals are. So we said 1 atmosphere is our average air pressure at sea level, and that's going to be equal to 14.7 PSI. Now, if you think about that, that means that at all times we have about 15 pounds per square inch on our body. If you were to hold 15 pounds, you're like, okay, I understand how much that weighs, but why don't I always feel that? Well, it's because it's our constant. So that's actually why if we go to another planet or another system, we need pressurized spacesuits, because that's what our body is like designed for, is for this constant pressure of about 15 pounds per square inch. Torr means millimeters of mercury, so 1 torr is 1 millimeter of mercury. 1 atmosphere is 760 torr, or millimeters of mercury, and 1 atmosphere is 101.3 kilopascals. I give you all these conversions here. All right, so why don't we practice this? So let's convert 1.75 atmospheres to kilopascals. So our conversion is 1 atmosphere is 101.3 kilopascals. So if we have 1.75 atmosphere, I'm going to flip that conversion factor. So we have 101.3 kilopascals over 1 atmosphere. So we can see atmosphere cancels. So you do 1.75 times 101.3, and you should get this answer of 177.3 kilopascals. So let's have you try now converting that to torr. So you can either use the atmosphere or the pascals you just identified. And your answer is given here. Oops. Your answer is given here. All right. So now that we know what pressure is and how to deal with it, we also we're going to go through some basics of some other terms and like things you're going to need in order to get through this unit. When we're dealing with gases, we need to consider the volume, temperature, and pressure, and that's going to be dependent on the environment. So we actually have something that we call like a standard environment, and we call it STP, and this stands for standard temperature and pressure. For standard temperature, that's 0 degrees Celsius, which is 273 Kelvin. And standard pressure, we already talked about being 1 atmosphere. Now I pointed out, right, that we have Kelvin there. So actually, when we use gas laws, we have to use Kelvin as our temperature. But you're often going to be given that temperature in Celsius. And so this is how we convert to Celsius from Kelvin. From Celsius to Kelvin. So if you're given the temperature in Celsius, you're just going to add 273 to it, and that's going to be your temperature in Kelvin. To go the other way, so if we want to find the temperature in Celsius, we would take the temperature in Kelvin and just subtract 273. So let's have you try, so let's do that with Celsius going to Kelvin and then Kelvin to Celsius. So for 23 degrees Celsius going to Kelvin, we're going to add 273. And so that is 296 Kelvin. So let's have you try the next three. All right. So for the first one, you should have gotten 257 Kelvin. For the second one, you should have gotten 168 Kelvin. And for this third one, you should have gotten 408 Kelvin. All right. So now let's go the other way. Let's convert from Kelvin to Celsius. So remember here, we're going to be subtracting 273. So for this one, we will do 237 minus 273. And so we get negative 36 degrees Celsius. So let's have you try these next ones. All right. So for this first one here, you should have gotten negative 113 degrees Celsius. For the next one, you should have gotten 27 degrees Celsius. And for this last one, you should have gotten negative 67 degrees Celsius. And so what you can see here, right, is when we have Kelvin, we're always going to deal with whole numbers, and that's why we use Kelvin instead of Celsius when we're in the next couple classes when we talk about gas laws. Kelvin is actually the measure of movement and relating to that idea of the kinetic molecular theory. So that's part of the reason why that's why we use Kelvin instead of Celsius. It's just that we're typically going to be measuring the temperature in Celsius, so we need to know how to convert it. All right, so let's talk about how we measure a gas. Why wouldn't we weigh it or take the mass of a gas? Why would that be difficult? So hopefully you came up with the idea of because gases take up a lot of space and are very light, weighing it is going to be really difficult to do, and it's not really that practical. So what would be a better way to measure it? Hopefully you came up with volume would be a better way to measure it. And that's actually what we do. So what scientists have learned is that 1 mole of any gas at STP, so at that standard temperature and pressure, has a volume of 22.4 liters. And this is truly any gas. So it doesn't matter if you have a really small gas, so if you just have helium on its own, or if you have a really big gas like octane, that's what you use to run your car. At standard temperature and pressure, so at 1 atmosphere and 0 degrees Celsius, it's going to take, if we have 1 mole of it, it's going to take up 22.4 liters of space. That would be about 11 2-liter bottles of cola. If you're in the classroom, that big mole that is has like the My Little Pony fabric, that's about 22.4 liters, right? It's 1 mole, a molar volume there. And the black cube also, that's 22.4 liters, so that you can get an idea of that. Now remember, this is at 0 degrees Celsius and 1 atmosphere, so you might think like, so sometimes that's hard to envision, like how would we fit like 1 mole of gas in there? How would we fit that many molecules in there? And it's because it's going to be at a much colder temperature than we're currently at, even though we're close to 1 atmosphere. So just like how we use molar mass to convert between moles and grams, we can use molar volume, and that's what we call this, molar volume, to convert between moles and liters. So let's do some practice with that. So if we have 3 moles of oxygen at standard temperature and pressure, we want to know how many liters is that. So we're going to take 3 moles, and for every 1 mole, that's going to take up 22.4 liters. So you're going to do 3 times 22.4, and you should get 67.2 liters. So let's have you give this second one a try here. All right. So with this one, you were told the volume is 3 liters, and you're looking for how many moles. So we're going to do 3 liters. And for every 1 mole, we have 22.4 liters. So we're going to do 3 divided by 22.4, and you get 0.13 mole. All right, so that's pressure and then a few things that we need for solving problems here.